So today I will mostly devote like 90% of the time on stability derivatives. And then if I have time, then I'll cover some properties of the second order differential equation and why it is related to pure pitching motion. Okay. So I'll go a bit fast today, stop me wherever you feel like. So up until now, we have seen that what concerns when we are looking at an aircraft is there are some outputs that we are concerned about. What are these outputs? These outputs are the forces, aerodynamic forces X, which includes thrust and drag. Then we have Y, which includes like side slip forces. And then we have Z, which is like the lift direction. And then we have moments, rolling moment, pitching moment, and yawing moment. By now you have studied the state space model of that has been introduced in the class. So we know that there are a few states, state variables, or I can say, and there are some things called inputs. Okay. Now what is happening with state variables? What are the state variables? My velocity values, both translational and angular, as well as u dot, v dot, and w dot. Okay. Similarly, in inputs, what do we have? We have delta aileron. Sorry, not aileron. Need a lot of space, so cram this together. And then in inputs, we have delta E, elevator, delta aileron, delta rudder, and delta thrust, right? And we can also have like alpha also as one of our state variables. Alpha dot could be also one of our state variables. You could like come up with more state variables, like if you have a different aircraft design, you could have a different set of state variables, but anyways, like this is more or less exhaustive. So what are stability derivatives? Stability derivatives, so until now we were doing static stability, now we are doing dynamic stability, right? So stability derivatives means that how does the output change given the current state and the input, okay? So as you can imagine that obviously there are primarily 6 outputs and there are like 9 plus 2 11 and 11 plus 4 15. So 6 times 15 you have to like be able to derive 90 stability derivatives, okay, which means that putting 90 stability derivatives on your cheat sheet is not going to help. So this is how a general methodology goes on. So this is like the most difficult question, like after this it's not going to be that difficult, but stability derivatives is one of the most physically demanding questions, as in you need to really dig into the physics of the problem. So where does the stability derivative thing arise in the first place? So remember that in linearization we made this claim that let's say I had the pitching moment and it was a function of all these state variables, right, as well as the inputs. So I can go ahead and write it as del m del u I could write this, linearize this del m del u about some reference point, okay, del m del u calculated at some u naught. Maybe I am analyzing climbing, maybe I am analyzing cruising, maybe I am analyzing landing, maybe I am analyzing a turn maneuver, but about some reference maneuver. And the reference maneuver is going to give you the reference values for the state variables. And further, the pilot might want to act to change the reference condition, then you would need inputs. Does that make sense? Yeah?
I'm concerned with the input for like the x and y. So I thought x was like delta L around, but y is like the delta elevator and delta thrust.
Oh, like you're saying dependency?
Yeah.
Yeah, we will see that. Like it's actually all related, but that's the part of stability derivatives. You need to study the physics to see that on what is the derivative like important, on whose is the dependence strong. So, for example, we linearize this about some reference condition, but to in all honesty, I would want to tell you that this is actually an approximation. Okay. Why is this an approximation? Because we use something called Taylor's expansion to write this expression. What is Taylor's expansion? So, let us say I had some random function and I was given the function values at some points, let us say at some reference point x naught, and I wanted to find or approximate an expression for the function in the neighborhood of, in the small neighborhood around x naught. So, Taylor came up with an expansion that you can write f of x provided that x belongs to this small neighborhood around x naught as f of x naught plus del f by del x at x naught times delta x, which is nothing but x minus x naught plus del f by del square f by del x square evaluated at x naught delta x whole square by 2 factorial, and this goes on to be an infinite series. Now, what happens is, because mostly in our physical, when we apply this to the physical world, this small disturbance that you see is below the order of 1, right? It is a fraction, and what happens with fractions? If you keep taking their higher powers, they are going to go vanishingly smaller and smaller, which means that maybe this entire term is equal to 100, but actually the first two terms are contributing 99 and the rest of the terms are getting progressively smaller. So, we say that we consider this to be higher order terms, you will see HOT written in a lot of books, and we ignore or neglect these higher order terms. And we go ahead and find out, okay, this is the main contribution, I will go and study the linear part of this. So, why do I want to study linear part of this? Because okay, second derivatives, third derivatives are fine, but at least I need to know the first derivative, that how does the function change with x. Now, what if f of x was also a function of x and y, right? Let us go to two variables. So, obviously, I will have to define it about a reference point x naught y naught plus del f by del x at x naught y naught times delta x plus del f by del y at x naught y naught times delta y. Now, the second derivative gets interesting. You have to take del f del square at the reference point times delta x square by 2 factorial plus del square f by del y square at the reference point times delta y square by 2 factorial. So, what is this expansion studying? This expansion is studying that I do not know the function, but I want to approximate it in a small region around the reference point. So, this could be your lift, this could be your side slip force, this could be a drag, this could be a rolling moment, anything, and these x and y are basically your state variables. So, I am saying that if I move a little bit away from x and y, then what is the change in the function? So, I need to know that how does the function change with x. If I move a little bit in the direction of y, I need to know how does the function change with y. Now, I know this, let us say, but further if I want to take like even further steps, I need to know how does this change with x and y, right? So I go ahead and find out that okay, del square f by del x square is del f del x derivative with x. Same with here, but now you have these additional terms. You have del square f, del x, del y. These are called mixed derivatives. What will happen? I am studying the variation of, so there are two things here. So del f by del y, studying the derivative with respect to x. How does this change when I move in x? And then how does this change when I move in y? But again, you see in the physical or engineering practical realm, these are again going to be very small numbers. So we are going to lump everything here and say these are higher order terms, and we are going to neglect them to 0. So the entire game of stability derivatives is to get these, the first order derivatives of a force or moment with respect to a state variable or an input variable. Okay. Now, how do we do this? So I will take one example. Let us say that you had an aircraft. These are its horizontal tail, this is its vertical tail, these are the wings. So what is the first thing that I need to define in terms of stability derivatives if I wanted to ask that, we are going to go ahead and analyze the stability derivatives of this? What is the first thing you need? You need a reference condition. So I will choose cruise as the reference condition, which means that this aircraft has some u naught not equal to 0, rest all of the state variables are 0, except maybe alpha naught is non-zero. Okay. Now, what happens? I have the CG somewhere here, and I get a disturbance in the yaw rate. I suddenly have a yaw rate now. So, what is going to happen? So, now the question will ask you, what will happen to x, what will happen to y, what will happen to z, what will happen to L, what will happen to M, what will happen to N, so on and so forth. So, you need to go in that direction to find out what to do with the question next. Okay. So, let me write down a small template so that you find it easy to navigate these questions. So, the template you can follow is, first of all, identify the reference condition and then identify output variable. So, let us say that the question is asking you, go ahead and find CNR and CLR, that is the stability derivative of the yawing moment with respect to yaw rate and the stability derivative of the rolling moment with respect to yaw rate. Okay. So, I have identified my outputs, which means that I need to look at yaw and roll, correct. So, now first let us look at yaw. So, what is going to happen in the yaw rate? How am I going to analyze that what's going on with the yaw rate? Hmm?
There, like, community decided explicit formula for the
Stability derivatives is one of the questions where you can never get away without making a sketch. If you are not making a sketch, you are definitely going to do a blunder. Why sketch? What are the components we have? We know that we have studied about the wing, we have studied about the horizontal stabilizer, we have studied about the vertical stabilizer. So we will go and just look at what's happening. Okay, fine. Now because of the yaw rate, right, what's going to happen at the wing? If I take a certain section of the wing that was at a distance y from the fuselage reference line, earlier it was going with velocity u naught, but because of the yaw rate, now it is experiencing a lack of velocity ry, and the opposite effect will happen here. But we know that if we take care of the signs properly, when we integrate, everything comes together. So what's happening with the wings? Forget about C and CL right now. We just know that okay, we have to worry about those. But look at the disturbance and look at each component. What's going to happen with the wings? The wings are, so this wing is going to experience a drop in lift. This side of the wing is going to experience an increase in lift. Now this drop in lift or increase in lift, is it due to change in angle of attack? What is it due to? Change in velocity. So just make a note that wing is being affected by delta u, okay, which means that I am going to get a rolling moment. If we know that if we have different lifts on both sides of the wing, we get rolling, right? Not much contribution to yaw, because lift does not have any, wings do not have any much contribution in the yawing region. Let's go and look at the horizontal tail. What's going to happen at the horizontal tail? Same thing here, it was flying with u naught and now it will experience some ry, but you have to ask the question that should I bother comparing wings effect to horizontal tail effect, because what is the job of the horizontal tail? Is it a lifting surface or is it a control surface? It's a control surface, and the disturbance is coming from the wing in terms of lifting. So yes, the horizontal tail will contribute to some change in rolling moment. The horizontal tail also creates some rolling moment, but that rolling moment is very, very small in comparison to the rolling moment that would be captured by the wing. So by any approximation I can just simply ignore, and then I know that the horizontal tail obviously does not contribute anything significant to yaw. There are other contributors which are much more, contribute to yaw much more significantly. Now let's look at what's happening at the vertical tail. So this is the vertical tail V. Earlier it was having u naught, and let's say the distance from the CG to the vertical tail is given as LV. Okay. So the question might have LV, but you don't need to keep it in your head. When you make the sketch, you will be like, oh, I need LV, I need to go and look for LV. If LV is not given, not deducible, or something is not given or deducible like CL alpha, you can go and approximate it, but I am definitely sure that LV would be given. It's not something you can approximate. And now what's happening, that now you have a velocity RLV, correct? So what's happening in terms of physics? Angle of attack at the vertical tail is changing. So now we have a non-zero angle of attack, right? And I can call this like, so for this it's kind of a, if you look with respect to the entire aircraft, it's kind of a side slip, but if you look just with respect to the airfoil, it's angle of attack. So you just need to keep that in mind. Let me just call this temporarily as delta alpha or delta beta, doesn't matter. There is some change in angle of attack at the vertical tail, due to which what is going to happen? There is going to be a extra lift force on the vertical tail, and which means that okay, now I have the vertical tail and it has change in angle of attack. Is there any other component that I am left to analyze? No. Wing, vertical tail and horizontal tail, done. something extra that might be given to confuse you, maybe something is about the engine, something about something else, but fuselage we more or less neglecting this course. We have analyzed the 3 components. Now, the 4th step is doing the math. So, now I will pick up the first yawing moment. Is wing contributing to any change in yawing moment? No. Is horizontal tail contributing to any change in yawing moment? No. But this lift force multiplied with this momentum, it is going to. So, what is happening? I have, and I will do it in a generalized way, okay, completely generalized way, so that you do not face issues while doing homeworks. So, now if I go and look at the side view of the vertical tail, the vertical tail could be some general shape and its total height may be given, and this is some distance z, and the chord at this distance is c as a function of z and subscript v. If this is a trapezoid, excellent, you know how very easily if this is a rectangular, best case scenario. But if this is a complex shape with sweep and taper, then you need to use the formulae while doing the math. Okay. But I am going to keep it general, so that you do not feel, what do you say, like as if it was done specifically for one shape, and then you are not able to extrapolate the idea to general shapes and integrate it. So, I will leave everything in integral form, but I will make a comment about simpler shapes. So, so what is happening now? I need to, so this is a general shape, I can't make any comments about the entire shape. So, when I am analyzing a general shape, I need to go and look at a slice of the shape first, and this is of width dz, correct, and I have drawn the 2D profile for that slice here, which means that the change in like d of delta L. So, delta L I am considering the total change on lift on the vertical tail, and small d is the infinitesimal derivative. So, d delta L tail is going to be what? It is going to be half rho u naught square reference velocity. I mean, you can still do, I do not mind doing like u naught plus r y square, but again you know that u naught is going to be much larger than r y. So, ultimately you are going to end up neglecting r square y square and 2 u naught r y. So, it is fine, I can simply do u naught square times the surface area. The surface area is going to be C v at z times dz times CL alpha of the tail times delta alpha of the tail. If you want to look at it as a perspective of side slip, you could call this delta beta tail, I do not care. Okay. And what is this delta alpha? So, I have a triangle, this is delta alpha, this is RLV and this is u naught, and since delta alpha is very small, we know that tan delta alpha tail is going to be RY RLV over u naught, but because alpha tail is very small, I can say that tan alpha tail is approximately equal to alpha tail, which is approximately equal to RLV over u naught. So, I will plug this in here. When I go and plug this in here, what happens? I have a cancellation. So, this u naught goes away. So, now this was the change on a section of the vertical tail. Now, what will be the change in moment, yawing moment introduced by this? You simply multiply it by z. So, change in the yawing moment would be this entire expression. I would like to organize some things which are not functions of z. So, yeah. So, here should I write C capital L or small l? Small? Why? Yes. So, I am analyzing sectional lift. So, it has to be C small, which means that as I move across the vertical tail, this CL can change. So, it is a function of Z right now, remember that. So, I can't pull it out of the integral. R is not a function of Z, LV is not a function of Z, this is a function of Z. So, rho u naught R LV divided by 2, and I had to multiply this with Z. So, I will get CVZ times Z, oh yeah, I have CL alpha tail CVZ Z dz. Okay. And if I want to get the total change in yawing moment, what will I get? So, delta n is simply going to be integral from minus, not minus, 0 to ZV times rho u naught R LV over 2 CL alpha tail CVZ Z dz. Now, I can pull out the constants out of the integration, great, rho u naught R LV over 2. You can also pull out this, but when you pull out this out of the integration, remember it is going to be CL for the 3D wing. So, you need to use capital L. If CL is given, then you need to convert it to the 3D CL, and the remaining integral is CVZ Z dz. If you had now, if you had a rectangular wing, the chord will also come out of the integral because chord is a constant, and you are simply left with 0 to Z dz integral. Okay. Now, what happens next? The stability derivative is, so you need to remember something, that whenever we are doing the stability derivatives, you also need to non-dimensionalize them, as in like these all state variables, they do not have the same units, okay? And you are studying the variation of force or moment with respect to the state variables. So, stability derivative should have one uniform unit, or either it should be dimensionless, but it is not dimensionless, it is dimensional, but each stability derivative should have the same dimension at least. So, we need to make some normalizations. So, what are the normalizations? Whenever, so here I can note down the normalizations. Remember that it has to be force by velocity units. Okay. So, if you have force by velocity units, anything in the longitudinal plane will be non-dimensionalized by C bar, any physics of the lateral plane will be non-dimensionalized by B. So, what does this mean? I have a moment here, right, and I am non-dimensionalizing it by, I have to take the derivative with respect to R. So, first of all, yeah, so now I am going to do del n by del R, which is equals to what? If I take the derivative with respect to R, this is the only dependence on R. So, it goes away, it becomes rho u naught LV by 2 CL alpha tail times this integral inside the brackets. And let me just make sure that I am using the correct normalization. Yep. So, now because there is a moment here and angular velocity is per second, so yep. So, basically I say that I will non-dimensionalize this way R B, because yawing is a lateral plane phenomena. So, I am using B divided by 2 u naught. Okay. Now, what happens? It is simply dividing this thing B divided by 2 u naught. So, 2 u naught goes to the top, 2 gets cancelled, and we have rho u naught square L V by B CL alpha tail integral over C V Z d z. Okay. Any confusions or anything that needs more clarification? No? Okay, excellent. Now, let's move on to, what do you say? So, we have calculated CNR, right? But now we are going to calculate CLR, rolling moment. And what did we see? That the wing is contributing to rolling moment. But if you look from the behind of the aircraft, you have a vertical tail, you have these horizontal tail, you have the wings, and you have a change in lift. Here is the CG along this line, and this is Z, aerodynamic center of the vertical tail. So, what is happening? What is this going to do? It's also going to create a rolling moment. So, now you have two contributions to rolling moment, and you need to study both of them separately, and then you need to combine them to get the final stability derivative. So, if you, a few people asked me that, is the portion before the midterm going to be a part of the final? I can say no, but the concepts are still going to be there. You have done this, you decompose into effects of different parts, and then you sum them together at the end. That's what we have been doing from the start.
So over here, it's just the formula, right? Like over here, like from delta n to the derivative.
Yeah, so this is del n by del r, and yeah, this expression is called CNR.
Wait, so the top is to take derivative of.
So I found the total change in the yawing moment, and then I am saying that how does this change in yawing moment depend on r? Okay,
So
and then
derivative
with respect to r, yes. So CNR is literally defined as this. So it is 2 u naught b del n over del r.
Yeah, so that we need to know, right? Basically. Like,
What do you need to know?
like the formula. I mean, there's a list of formulas.
So that's what I told you. This you don't need to. Yeah, this you obviously need to know. I mean, yeah.
So we need, because that's just how community defined, right? Like,
Yeah. But a trick to remember it is that the unit would be in force over velocity, and if you are dealing with angular velocity, you would need a length as well. So whenever you are doing pitching moment, like whenever you are doing longitudinal or pitching related activities, C bar. Whenever you are doing lateral or rolling, then you have B, and the reference is always going to be u naught. Okay. So now let's look at CLR. So what's the story with CLR? I know that first of all there would be a CLR wing plus a CLR tail. So let's go and look at the wing first. So what did we see in the case of wing? That at a distance y with a chord length c as a function of y, some width dy, what is the change in lift? Change in lift at the wing, it's half rho this. So change is only due to the added velocity. Okay, so it's half rho ry squared, and what else? And also because I am looking on the right side of the aircraft, this y is positive and lift is decreasing, which means, but lift is up this way and it is in the z negative. So that is why I am not adding a negative sign here. Does it make sense? You have to be very cautious of signs. Half rho v squared s. What is s? C of y dy times CL alpha tail. CL alpha tail. I'm in love with the tail. CL alpha wing times alpha wing, and this might be non-zero, right? And we know that the effect on the wing is not due to change of angle of attack. So I can lump this entire thing together to just make it CL of the wing.
I'm still a little bit unsure. So, like for instance, Ry is like
Yeah.
naturally, and it's with respect to the wing.
Mm-hmm.
Okay, so it would be the moment times the the distance.
The momentum times the angular
Okay,
velocity
so that we
is
get
the
that.
change in velocity.
Yeah, so okay, so in this case we use cy dy instead of the previous case. We use something else. I think.
Yeah, because when we were doing that for the, I mean, we were doing the integration about the vertical tail. So that was the z direction.
Okay, so that was about the vertical tail, but this is about the wing, so we do cy.
So wing is in the y direction.
Oh, so vertical tail in the direction. That makes sense. Thank you.
Yeah.
Yeah, is that CLW uppercase?
Oh, yeah.
Oh, really?
I mean, yeah, thanks for pointing that out. Sorry, yeah. Yeah, but you are basically removing alpha from the picture and you are, because it's ultimately CL naught plus CL alpha times alpha. And again, this is not the total change, this is the infinitesimal change of lift on that wing section. Okay. Now, what is the rolling moment induced due to it? Simply multiply by y. So, and multiply by y to check that okay, there was a loss in lift, which means that it is going to roll this way. So, it is positive. Okay. So, still the signs remain the same. So, d delta L coming from the wing is half rho r squared, and I am going to multiply y and take it together with things. I am already going to like shuffle them up a little bit. Any confusion about how you went from y square to y cube? And why did I shuffle these? These are functions of y, these are not. Okay. Now, I want the total. So, delta L wing is going to be half rho r squared integral. What would be the integral limits?
0 to b over 2?
Mm-hmm. I mean, yeah, you could do 0 to b over 2, but then you would have to multiply 2 in the front. But just to be safe with signs, always do it from minus b by 2 to b by 2. And then you have CL alpha, CL wing, cy y cubed dy. You go ahead and bring this out of the integral, make it 3D. So, rho r squared CL wing divided by 2 integral minus b by 2 to b by 2 c of y y cubed dy. Okay. So, I have reduced one part and I can go ahead and take the normalization, and for normal this could be in your cheat sheet, like I very much endorse, go into your cheat sheet and look like what you are supposed to normalize with, because that is what I am doing, cheating and looking into Nelson. If I am correct, so this is still in the lateral plane. Oh yeah, simple, it will still be divided by RB by u naught. So, you have del L by del R is going to be, you simply take the derivative, because this is the only r square term, 2 comes out, 2 gets divided. So, you get rho r CL wing integral minus b by 2 to b by 2, this entire thing. And now, if you want to get CLR contribution of wing, you just divide this entire thing by RB over 2 u naught. Okay. So, we are done with the wing part, but we know that there is a tail part as well. So, now let us go and look at the tail part. Okay. This is the tail at some cross section here of length dz, because now I am, Zofu, pay attention, now I am looking at the vertical tail. This is the y direction, this is the wing direction.
Vertical tail?
Yeah, that is why I am saying pay attention. So, I am looking from the behind of the aircraft. Okay. So, this is like the auxiliary power units, you are looking from the back. These are your horizontal stabilizers, this is your vertical stabilizer, and you have the wings in the front. Okay. Now remember that what direction goes into the board? X body. X body inside, Y body here, Z body here.
Oh, X body is the, okay.
Yeah. So that is why I am going to say that if this is the Z0, then at some distance Z, I have a section of width dz, and again its chord is going to be Cv as a function of Z. And we had already derived the expression for lift, actually change in lift. So we can go back to that. So recall that the change in lift is going to be the same, right? But what was the, yeah, you guys, I made a disaster here and no one noticed. So the moment term for the yawing is going to be LV. So you are going to multiply it with LV, L square V, L square V, L square V, and this is going to be CZ dz, CZ dz. Sorry for that, yeah, because now you will have CZ times Z.
L squared V.
Don't you need Z to get the surface area of the?
Huh?
Don't you need Z to get the surface area of the?
No, I'll repeat this again. Half rho u naught square is the dynamic pressure head, surface area is cot times dz, and then you have CL alpha tail times the local angle of attack. This was the lift expression. To get the moment, to get the moment expression, you need to multiply this lift with this moment term, which is delta L, which is LV. So it's my bad, I was supposed to multiply an LV here. But now same thing, half rho u naught square CZV dz CL alpha. So I can copy that as it is, no problem. So I can write down delta L tail is going to be half rho u naught square CVZ dz CL alpha tail small l R LV over u naught. Now if I want to go and find out the, so this is like infinitesimal change in lift. Now if I want to go and infinitesimal change in rolling moment because of the tail, I am going to multiply this DL tail with LV? No, I am going to multiply it with Z now, because now my moment term in the rolling direction is Z. So you go ahead and multiply Z, and then you do the same process that we did here. You go ahead and integrate to finally get like the total change in rolling moment is going to be integral. I'll just start pulling out things. So like half u naught cancelled, R will come out, LV will come out. So rho u naught R LV, I can pull out CL alpha capital L, and then now inside divided by 2, and now I have 0 to Z max, whatever is the height of the vertical tail, times CVZ times Z times dz. Okay. If you have a rectangular thing, then the chord can also come out, but if you have a trapezoidal or a wing with sweep and taper, then you will have to put in the complex formulas, geometrical formulas. So what is the next thing I have been asked? CLR. So what is the derivative I am supposed to take with respect to R? So you go ahead and take del L by del R, you get rho u naught LV CL alpha tail by 2 times, I will call this I1, times this integral I1, and then you go ahead and normalize it, because you need to add both the contributions, they should be in the same dimensions. So you go ahead and divide it by RB over 2 u naught. So you put RB and 2 u naught here, this gets cancelled, hence CLR due to tail is rho u naught square LV CL alpha tail I1 by RB. And now you are going to sum them up to write CLR is going to be CLR wing plus CLR tail. Is this clear to everyone?
Yeah, I mean, but I think the difficult part to think
Oh, the entire thing is difficult. There is no difficult part here.
Okay, but like,
Yes.
I mean, the somewhat non-intuitive part to me
Yeah.
was like, so like, because we have rudder, so like, I mean, it's fair to assume that rudder has to deal with the direction, or I need to deal with like the vertical tail. But like, I think it's difficult to say like rudder also depends on wing. That's not very intuitive for me to think.
Oh yes, you have to make use of that intuition. We actually made, you are right, we made use of that intuition. Why did we not consider the horizontal tails effect?
Probably because it's the axis.
Because what was the reasoning? What is the purpose of the horizontal tail?
Stabilized pitch.
Huh?
So stabilized pitch.
Okay.
Yeah, it's made for controlling the pitch. It's not for lifting the aircraft.
Okay.
But if you had a really weird aircraft where you had something like this and the horizontal tail was this size, God forbid someone makes this someday, but if you had, you could not ignore it.
Okay.
And then you also had to take into account a lot of other things. You would have to see that the downwash here will also become like the downwash being experienced at this would also become a function of r. So, when you go and write down the tails contribution, there is a 1 minus d epsilon by d alpha term, you would have to cast that in terms of r. But here we do not do that analysis, because we know that it is not there for lifting, it is for pitch control. So, you might get some small, that like obviously like your aircraft is like not completely unaffected, but it is such a huge body that if you apply a force of 1 Newton over like a 1000-ton vehicle, it is not going to notice it, you are not going to feel it as a passenger. Any other questions before I close the session, because I do not have time for second order differential equation, I will take that up together. No questions? Okay.